Hi dear students, our next topic in this unit is currents. Currents means the linear surface and volume current density. In this section, we will also discuss what is the magnetic force on current carrying wire, on the surface current, and also on the volume current. So current is nothing but current. Generally, we call current I is equal to rate of flow of charge, that is dq by dt. First, we will discuss what is the linear current density and what is the magnetic force on a current carrying wire having the linear charge density lambda. That is, our first one is the linear current. We know that a conductor contains large number of free electrons. All these free electrons are in random motion, and when connected to a potential difference, that is a voltage source, then the electric charges, this free electron starts to move through the conductor, that constitutes a current. Fine. Here, first we talk about the linear current density. For this, we can consider a conductor having the total length L and its small length is dl. Consider a small segment of the length of this wire. This lambda is the linear charge density. You can write lambda is equal to dq by dl. Fine. There is this line charge lambda is flowing through this conductor with a velocity v. Fine. From this expression, we can write dq is equal to the amount of charge that is flowing through the small length element dl is equal to lambda dl. As I mentioned, our aim is to find out the current, that is current I is equal to dq by dt. Fine. If consider this v is the velocity of the charge moving through the length dl within a time interval dt. Then that velocity can be written as v is equal to dl by dt. Fine. Or here this dl can be written as v dt. Our aim, as I mentioned, that is to find out the current in each case, that is dq by dl, or dq by dt. Then the lambda we had dq by dl, this dq can be written as lambda dl. Here I replace this dq by this expression, that is, this is a lambda dl by dt. We have seen here that this dl by dt is nothing but the velocity. Therefore, we can write this lambda instead of dl by dt, we can write this is a v. Fine. Or this current can be written as I is equal to lambda v. This is the current flowing through the wire having the linear charge density lambda. Now, if I keep this wire in a magnetic field, then what will be the magnetic force on the current carrying wire? That is our next discussion. Magnetic force on a current carrying wire. Since our wire consists of charge density lambda, and in a small length element dl, the charge flowing through this wire is dq. Then if this wire segment is kept in a magnetic field, P, then what is the force on this charge dq? That charge is moving with the velocity v. That is the magnetic force on the charge contained by the small length element dl. That force is given by df. df is equal to dq into v cross p. Here, this dq is the charge contained by the small length element dl. The dq can be replaced by this expression, that is lambda is equal to dq by dl. dq can be written as lambda dl. Therefore, thus df can be written as lambda dl into v cross b. Here I write the lambda and v together, that is lambda v into cross b dl. Just now we have seen that this lambda v is nothing but the current I. Therefore, this df can be written as I cross b into dl. This is the small amount of force acting on the length element dl. Now, what is the total force on this wall charged wire? If L is the total length of the wire, then what is the net force experienced by this wall wire? The total magnetic force acting on the wall length of the conducting wire. That force is F. Just we have to integrate this expression from 0 to L. That is line integral I cross B dl. This is the total force on the wire. Now let us go to the surface current density and the force on the surface current density wire. The surface current density is denoted by K. If we consider a charge flow over a surface, that is in this picture this is a surface through which a current is flowing this direction, and the surface current is K. That is, this K is the amount of current flowing per unit length in a direction perpendicular to the current flow. I repeat, K is the amount of current flowing per unit length in a direction perpendicular to the current flow. That is, this K can be written as the current, that is dI, flowing per unit length, that is that length is perpendicular to the current flow. Okay. This is question number 1. To make it more clear, I will draw another picture. Look at this picture. This is a sheet through which a surface charge is flowing. Sigma is the surface charge density, whose unit is coulomb per meter square. This surface charge is flowing through this charged sheet, and its direction is given by this. This is the amount of current, that is the flow of charge, rate of flow of charge through this conducting sheet. Now consider a small length element that is perpendicular to the direction of the current flow. I take a small length element. Here, this length is exactly the length perpendicular to the current flow. This I can write. This is the length dl perpendicular. Then the other side, this side is the length of the strip parallel to the current. Therefore, this is the DL parallel. DL parallel means this is a length element that is parallel to the current. Our current is flowing in this direction and the current flow is in this direction, and this length element is parallel to the current. Here also our aim is to find out the current. Current is given by dq divided by dt. First we are defining what is the surface current and an expression for the surface current in terms of the surface charge density sigma. For this, we consider a small area of the current carrying strip, that is, let us call the small area as a dA. That is, this dA is the small area of the current carrying strip. Let me write here, if dA is the small area of the current carrying strip, then that dA can be written as, it's very clear that this area dA is equal to length into breadth. That is dl perpendicular into dl parallel. Because the length of the strip is dl perpendicular and the breadth of the strip is dl parallel. That is, this is equal to dl perpendicular to dl parallel. dl parallel is the length of the strip parallel to the current flow. dl perpendicular, that is clear, that is the length of the strip perpendicular to the current flow. Therefore, our expression for the current, that is di is equal to dq by dt, and we know that sigma is equal to surface charge density coulomb per meter square, charge flowing per unit area, that is dq by dA. This sigma is equal to dq divided by this area, that is nothing but this quantity area, that is dl into dl parallel, dl perpendicular into dl parallel. Fine. Or I can write this dq is equal to sigma dA or sigma dl perpendicular into dl parallel. That is di is equal to, I substitute, I replace this dq by this expression, that is sigma dl perpendicular dl parallel. This will be equal to sigma dl perpendicular into dl parallel divided by dt. Now if you check this figure, that is, it's very clear that the charge is flowing in this direction and the length element parallel to that current flow is, or the charge flow is this dl parallel. Therefore, the velocity of the charged particle is the distance traveled by the charged particle in a certain time. That is, we can write that velocity v is equal to length by time, the dl parallel divided by dt. I can replace this dl parallel by dt by, that is the velocity of the charge that is flowing through the sheet, that is di can be written as di is sigma dl perpendicular into v, where v is equal to dl parallel divided by d. Let me put this is equation number 2. Now, if you compare to this equation 1, this equation, here we have to substitute the di, that is the di, we have turned this is di, that is put this equation 2 in equation 1. Therefore, our K can be written as surface current density, that is di by dl perpendicular, that is nothing but equation 1, that is equal to sigma dl perpendicular v divided by dl perpendicular. Here the dl perpendicular will cancel. We are left with sigma v. That is the surface current density can be written as K is equal to sigma v. This equation has to be remembered. Now, if we keep this charge flowing sheet or the current carrying sheet in a magnetic field, what is the magnetic force on the surface current? That is our next topic. Here we consider a surface carrying current placed in a magnetic field B. Here we consider a surface carrying current is placed in a magnetic field B. That you assume that this sheet that is kept in a magnetic field B. What is the force on this surface current K by this magnetic field B? That is the next discussion. The force on a single charge Q that is moving with a velocity v in a magnetic field B is given by this F is equal to Q in the v velocity. Then the force on a dq charge that can be written as df is equal to dq into v cross b. Fine. The sigma is, we know, dq by dA, or this dq is equal to sigma dA. Therefore, this df can be written as sigma dA into v cross b. Fine. I take this sigma with v, that is, this will be sigma v cross b into dA. Here this sigma v is nothing but the surface current K that just now you have seen. This is the surface current K sigma v. Therefore, this can be written as K cross B into dA. That is our dF, where this K is sigma v. Fine. This is the force experienced by a small area dA. Then the total force experienced by the entire surface carrying current, then that can be written as F. Just integrate the above expression. From where to where the surface area we have to integrate? That is K cross B dA. This is the total force on a sheet that carries a surface current K and kept in magnetic B. Fine. Now, in the similar way we discuss the volume current density and the magnetic force on the volume current density. Here we consider a tube, and this tube has an area that is perpendicular to the current flow. J is the volume current density. Then that volume current density J can be defined as the amount of current flowing through unit area in a direction perpendicular to the flow of current. J can be defined as di by dA perpendicular. That is amount of current flowing through unit area. If the current is flowing in this direction, current flowing through unit area in a direction, the current is flowing in this direction through a unit area dA in a direction perpendicular to the current. This area is perpendicular to the direction of the current. This J can be defined as the amount of current flowing through unit area in a direction perpendicular to the flow of current. Here also we define the current di, that is the rate of flow of charge dq by dt. This tube has a certain volume V. Let d tau be the small volume element in this tube, and it contains a charge that is dq. Then the charge density can be written as dq by d tau, or we can write rho is equal to dq by d tau, or dq is equal to rho dt. Here, if I consider a very small volume element that is called d tau here, consider in this tube, then that d tau is nothing but the area into breadth or length. That length that is parallel to the current flow. That length of the small cubic element is that is parallel to current flow is dl parallel. Therefore, this d tau can be written as dA perpendicular into dl parallel. This di is equal to dq by dt, means I substitute this value here, that is rho into dA perpendicular into dl parallel divided by dt, or this is equal to rho dA perpendicular into dl parallel. This is a length element parallel to the current flow. The displacement of the charge that takes place along the direction of this length element. That's why we have taken dl parallel, that is divided by dt, and we have seen that dl parallel by dt is nothing but V. That is di is equal to rho dA perpendicular into V. This V is the velocity of the charge. dl parallel divided by dt is the velocity. Now, if you go back, this was our expression to find out the volume current density J. Therefore, now we have derived an expression for di. Then substitute that di to that expression. Is J is equal to di by current flowing per unit area in the direction perpendicular to the current flow is di by dA perpendicular rho dA perpendicular to V divided by dA perpendicular. These two cancel out. Now we are left with rho V. Therefore, the final result that we are obtained is J is equal to rho V. This is the volume current density. Fine. Then what is the magnetic force on this volume current? That is, we can start with F is equal to Q into V cross P, which is the force on a charge Q. Then the small amount of force on a small amount of charge Q, or the force on a smaller amount of charge Q is given by dF, which is equal to V cross V. As usual, we define rho is equal to dQ by d tau. Then we will replace this dQ is equal to rho d tau. This is equal to rho d tau into V cross P. This is equal to rho into V cross B d tau, or I write the rho with the V. This is rho V cross B into d tau. Now we have seen that this rho V is nothing but the current density J. Therefore, the dF can be written as J cross B into d tau, or the total force on this current carrying tube is equal to F is equal to volume integration J cross B into d tau. Now you are familiar with the way how to find out the total force of the linear current density, or the surface current density, or the volume current density. Fine. If you summarize three cases that we have discussed so far, I is equal to lambda V. This is the linear current, and the force on this linear current is equal to line integral I cross V ds. The surface current, that is equal to K into sigma V. The force on the surface current is K cross B dA. Similarly, the volume current density we have defined rho V. Then the force on the volume current is volume integration J cross B d tau or dV. You can choose whatever you want. Fine. I hope this is clear to you. Thank you very much.